To carry out this experiment, we need dry ice, tongs, 2 100 milliliter beakers, pot holders, Bromthymal blue, and water. In this experiment, we will dissolve solid carbon dioxide, commonly known as dry ice, in water to create carbonic acid. To show the change in pH due to a formation of acid, we will use the indicator Bromthymal blue. In a beaker of water, the indicator will make the solution appear blue. When acid is formed, the solution will turn a yellow color, indicating a change in pH. As the carbon dioxide sublimates, carbon dioxide gas molecules are cold enough to cause the water vapor in the air to condense into small droplets and form a cloud surrounding the reaction beaker. Notice how this cloud flows over the beaker before sinking. This sinking can be explained by considering the molar mass of carbon dioxide in air. When broken down, air is 78% nitrogen, 21% oxygen, and a 1% mix of argon, water vapor, and other gases. This makes the average molar mass of air 29 grams per mole, whereas carbon dioxide's molar mass is 44 grams per mole. Since molar mass is proportional to density for a gas, we see that carbon dioxide is denser than air, allowing it to sink. As expected, the indicator changed from a blue color to a yellow color seen here.
As we will learn later, the K value of this reaction is incredibly small. This means that the reactants are favored. As we can see here, the water level remains relatively constant, and there is way more water than carbonic acid formed. So far, we have seen what dry ice does on a small scale. Out of curiosity, we decided to see what would happen on a large scale.
Adding a greater amount of dry ice to a greater amount of water makes the sinking of the water vapor even more apparent as it sinks into the sink. The visual effect created is often utilized on Halloween and at concerts.
In our small-scale experiment, we were able to witness the full duration of the reaction. Because of the larger volumes in this large-scale experiment, we were not able to see the complete reaction occur.
Even when you scoop the vapor out of the sink, it still sinks into the bottom of the cup. After illustrating the density concept, we wanted to see what would happen if we placed a substance inside the solution with the carbonic acid. We chose to use Skittles to watch the outside of them and see what would happen. As you can see, the outside coating of each Skittle completely dissolved in the carbonic acid.
The carbonic acid formed in this experiment has a structure like this, with the carbon atom in the middle having 3 charge clouds and no lone pairs, giving it a trigonoplanar structure. The carbonic acid has a molecular weight of 62.024 grams per mole. It is odorless and has no boiling point, as it will decompose as the temperature increases. There are 2 single bonds on the central carbon atom and 1 double bond, and these do not cancel each other out, making the molecule polar. Because of this, this molecule is soluble in water. As in all molecules, this molecule contains London dispersion forces. These may be weaker than other molecules that have greater molar masses. As I previously stated, this molecule contains some polar bonds, giving it dipole-dipole forces. Additionally, the oxygen and hydrogen create a hydrogen bond, giving this molecule hydrogen bonding. The pH of carbonic acid is 4.68, making it a relatively weak acid. This means that the H+ ions will not ionize completely. This would make carbonic acid a good acid to use in titration. The reaction in the experiment we are conducting is composed of the reactants water and solid carbon dioxide, or dry ice, yielding the product carbonic acid. The K-value of this reaction is 1.7 times 10 to the negative 3, meaning that if we were to not intervene, there would be relatively few products.
The dry ice is at a temperature of negative 78 degrees Celsius. This is cold enough to cause serious frostbite, and we had to be careful to handle the dry ice with tongs or have it wrapped in a pot holder while performing the experiment. Touching dry ice for longer than a brief period of time hurts, as the endothermic process of sublimation takes heat from your hand. However, we were able to touch the cloud formed during the reaction for extended periods of time without being harmed. This is because the condensation of water is an exothermic process. Since the endothermic sublimation and exothermic condensation of water are happening at the same time, their enthalpies essentially cancel out and cause very little overall environmental temperature change. Thus, it is safe to hold your hand in the cloud for as long as you want.
Carbonic acid serves a vital role for living creatures, specifically mammals and their blood. Carbonic acid works as part of an acid-base buffer known as the bicarbonate buffer system, which involves the balance of carbonic acid, the bicarbonate ion, and carbon dioxide in order to maintain pH in the blood and to support proper metabolic function. It occurs when carbon dioxide reacts with water to form carbonic acid, which in turn rapidly dissociates to form a bicarbonate ion and a hydrogen ion. As with any buffer system, it consists of both a weak acid and its conjugate base. While the body contains other buffer systems to control pH in the body, the bicarbonate buffer system is the only one that works with the respiratory system. After breathing, carbon dioxide is produced as a product of cellular respiration. Some of this carbon dioxide begins to get dissolved into the blood, where it can react with the water that is already found in the plasma. The water and carbon dioxide react within the body to form carbonic acid first. Some of the carbonic acid decomposes into hydrogen ions and bicarbonate ions. Thus, both bicarbonate ions and carbonic acid molecules are now present in the blood. This reaction would take a very long time without a catalyst. Fortunately, an enzyme known as carbonic anhydrase speeds up this reaction by lowering the activation energy needed to form bicarbonate ions. This allows the reaction to occur at a reasonable rate in the body. The carbonic acid, as a weak acid, has the ability to neutralize any process that attempts to alkalize the blood. Bicarbonate, as the conjugate base of the carbonic acid, has the ability to neutralize any process that attempts to acidify the blood. If the pH of blood ever drops below 7.35 or above 7.45, serious illness or death can occur. Many things can lead to the acidosis of blood. Among these include alcohol or drug use, overuse of antibiotics, shallow breathing, excess animal meats in the diet, food coloring and preservatives, processed and refined foods, not enough fiber, chronic stress, or lack of exercise. Fortunately, due to the buffer system, many of these activities alone do not cause a long-term effect on the pH of your blood. What may lead to a long-term increase in the acidity of the blood, though, could be poor lung function, as poor lung function can cause a buildup of CO2 in the blood. As we know from Le Chatelier's principle, the addition of a reactant will cause the entire process to favor the production of more products. Because of this, more H2CO3 will be created and the pH of blood will continue to drop. Symptoms of metabolic acidosis include nausea and vomiting, shortness of breath leading to one breathing deeper and faster than normal, and chronic migraines or long-lasting headaches. The average and healthy pH for blood is slightly alkaline at 7.4 on the pH scale. The pKa of carbonic acid is only 6.1 at physiological temperatures. Using the Henderson-Hasselbalch equation, the ratio of bicarbonate ions to carbonic acid can be determined. In the equation, we can set the pH of blood equal to the pKa of the carbonic acid plus the log of the concentration of the bicarbonate ions over the concentration of the carbonic acid. Since we know the ideal pH for blood, we can substitute 7.4 in for the pH, and since we know the pKa of the carbonic acid at body temperature, we can substitute 6.1 in for the pKa. We can then subtract over the 6.1 to get that 1.3 is equal to the log of the concentration of the bicarbonate ions over the concentration of the carbonic acid. By taking 10 to the power of each side, we can isolate the ratio between the concentrations of the two substances. From this, we can conclude that in blood there needs to be a 20-to-1 ratio between the bicarbonate ions and the carbonic acid molecules. This essential reaction is not only restricted to the blood. It also occurs in the bladder, epidermis, intestines, kidneys, nerve cells, pancreas, placenta, thyroid gland, and skeletal muscles. In all, we can thank this simple reaction from water and carbon dioxide for the life we live today and our ability to have a stable pH in our blood.